Okay, welcome back. Good to see you. It's Monday, June 29th. We are moving along. This is Chapter 18, Part 1, Electrophilic Aromatic Substitution. This is the last chapter, believe it or not, before Test 1. So we need to remind you of that coming up. Quiz 2 is due tomorrow. After recitation, here's what it looks like. It's 5 problems. There is a ChemTube problem in there. It's on Learning Suite. The PDF is under the content. Make sure you print that off, fill it out, scan it, and upload it. And also on this quiz is a questionnaire. We'd like you to fill that out and upload that so we can get to know you a little better. So do that by Tuesday here. Test 1 will be Monday, July 6th, after the July 4th weekend. So don't party too much. Be ready for the test. Chapters 16 through 18 there. There's a sample test already on Learning Suite, sample test 1, and we'll use that for the review and whatever other problems you'd like us to review. Of course, bring your specific problems to recitation and office hours, and we can help you out with all that. All right, Chapter 18. Let's look what we're up against here. We've got 5 new reactions, and that's the key here. And all of these electrophilic aromatic substitution, what does that mean? It means the reagent is electron poor. It's electrophilic, and it's going to pull 2 electrons out of the benzene ring, okay? And it's going to give this cyclohexadienyl cation intermediate. This is going to be the same intermediate for all 5 reactions. So you got to focus on this key mechanistic pathway here. And then instead of having a nucleophile add here like we'd had for all the additions to alkenes in 351, this now can easily become aromatic again, you see, by loss of the proton off that same carbon position where the electrophile goes on. And we re-aromatize. And remember, that's 30, 35 kcals per mole. That's a very stabilizing effect. So instead of the addition there, where you lose aromaticity, here you can use the base, pull the proton and go back to the benzene ring, okay? So here are the reactions. There's 5 of them. We'll handle them sequentially. You need to know the mechanism of each one. The real key here is knowing what the true electrophile is for each one of these new 5 reactions. And these are workhorse reactions in the lab and in industry. These are done on ton scale worldwide. So these are very important reactions, transforming benzene, which is obtained where? From coal tar. You crush coal and you steam distill it, and you can get a lot of benzene. It's a very cheap material, okay? And you can take benzene then, treat it with nitric acid, sulfuric acid, and get nitrobenzene. We call that nitration. Now looking at those reagents, nitric acid, sulfuric acid, what's the electrophile? Well, we'll get to that in a second, but that'll be a key part of the mechanism, okay? And those are pretty harsh conditions, right? Nitric acid's a strong acid, sulfuric acid's a strong acid, so that's really bringing it on reaction-wise, and you create the nitrobenzene. Okay, also for sulfonation, you create the benzene sulfonic acid here. You need to draw that out, maybe sulfur with 3 oxygens around it. There's 2 doubly bonded oxygens and then 1 hydroxyl oxygen. It is an acid. It's like sulfuric acid, similar to tossic acid that maybe we've talked about before, making tosylates, tosyl chloride. This is related to that. This is the benzene sulfonyl sulfonic acid, not the paramethyl toluyl one, which just has a methyl group here. But you'll see the similarity there. It's just sulfuric acid, or it's sulfur trioxide and acid. Either way can make the sulfonated product here. The other reaction, the next one, is halogenation. I've already mentioned this. We're reacting with bromine or chlorine, so X2 here, molecular halogen, with a iron halide catalyst. If you don't have that iron halide catalyst here, you get no reaction. So it's very important you focus on the reagents for the reactivity part, and then you get the monohalogenated product. Again, that's different from an alkene. And then we have the 2 Friedel-Crafts reactions, named for the chemists who developed this. Friedel was a French chemist. Crafts was an American postdoc in France. And these reactions are very important because they form carbon-carbon bonds. We have alkylation via the alkyl halide in the aluminum Lewis acid to form alkylated benzenes. And then we can acylate it and put a ketone on there from the acid chloride. Now, maybe that's a new functional group that you haven't seen before. We'll have to show you what that is. It's just a carbonyl with a chloride on the side. The chloride can be a leaving group with the Lewis acid that's pulled off. And you'll see what the true electrophile is here in a minute. And that gives the aromatic ketone product. Now, there are some corollary reactions in this chapter. Maybe I kind of lied there to say there's only 5. There are a couple more, sorry. We can reduce the aromatic ketones under the Clemmensen conditions with zinc amalgam and HCl, or the Wolff-Kishner reaction with potassium hydroxide and hydrazine to go from the aromatic ketone to the alkylated benzene. Now, you might say, well, we've already got an alkylated benzene route here, Friedel-Crafts alkylation. Well, these go with rearrangements if we do them directly. So you'll see some caveats, some limitations to Friedel-Crafts alkylation. If we want to have the non-rearranged product here where the primary carbon stuck on the benzene, we have to go through the aromatic ketone and then reduce it under either conditions, either the acidic conditions or the basic conditions to get to the non-rearranged product. Okay, if that was it, chapter 18 would be a breeze, right? You could handle 5 new reactions. But we're going to up the ante here and do dye substitution. So we're already going to have a group on the benzene, and we're going to put another electrophile on there. We're going to have donor groups, which are typified by alkyls or heteroatoms that have lone pairs next to the benzene that can donate electron density into the benzene. We call these activators. They're faster reacting reactions than benzene itself, and they give ortho and para products selectively. And the only way you're going to be able to understand that is to examine the intermediate allylic cations. We're going to do that and go through some activities to make sure we reinforce it. So donor groups react faster and they give ortho-para products. We can almost always separate those two products. I'm not going to make you remember what percentage of ortho versus para. It's often a mixture that you can easily separate by crystallization. Now, if we have an electron withdrawing group already on the benzene, that's down here, EWG, sorry about the abbreviations there. These are groups that are electron deficient. In fact, ammonium and nitro have full-blown cations right next to the benzene ring. So you see that's pulling electron density out. Those will slow down a second electrophilic aromatic substitution, and they will selectively give meta products right here, 1,3 products. So we'll have to again examine the allyl cation intermediate, and here with the withdrawing group, if we go meta, the cation is always opposed to or away from the carbon bearing the electron withdrawing group. So it deactivates all 3 positions here, ortho, meta, and para, but it deactivates the meta attack to a lesser extent. So even though it's slowed down, it's a little bit faster than the relative ortho-para reactions, again, if you have the withdrawing group. Okay, so yeah, this is leading to the product that's not observed if the cation's placed right next to that group. And again, that'll be more clear when we get to that. We will do the flipped approach here, nucleophilic aromatic substitution, where you have a leaving group on the benzene that can be pulled off. You have to have an electron withdrawing group to activate that halide as a leaving group. With strong base, we can make benzyne. There's a funny name for you. What does "ine" mean? Triple bond. Yeah. Can we have a triple bond on the side of a benzene ring? Yes. With a strong enough base, we can make what's called benzyne. And maybe if we don't have enough time, we may leave that out. So don't be disappointed if we leave out benzyne. But you can read about it in the book. I don't think I normally put it on a test. Sometimes it shows up on ACS exams. So it's kind of an extra topic that way. And then, yeah, there's a radical reaction here, benzylic halogenation. This is like allylic halogenation we saw before in chapter 15 with NBS and peroxide. Here you can do it with light and bromine or chlorine. And at the benzylic position, you have to have at least 1 benzylic hydrogen to substitute there. You can get the benzyl halide at that point. And you can do other things, substitution, elimination, whatever. But it's a way to selectively make that. And because the benzyl radical is a stable pathway. We can also take an alkyl benzene and treat it with chromic acid. Now again, this is not sulfuric acid. This is not HCl. This is chromic acid. This is strong acid, but there's chromium in a high oxidation state. This will actually cleave carbon-carbon bonds and make benzoic acid of any type of alkyl group there. As long as it's primary, secondary. Tertiary, if there's a tert-butyl group here, the chromic acid will be not reactive. So we won't do the full mechanism of that. We'll show you the mechanism of halogenation. And then yes, we will do synthesis, multi-step synthesis, show you how to make some complex materials, some common materials you've probably heard of before. We'll make use of this aryl ketone to the alkyl benzene, and we'll also make use of a reduction reaction of the aryl nitro functionality to the aniline. Now aniline, that's a parent name I wanted you to remember nomenclature-wise, right? What's aniline mean? Right, aminobenzene. And we'll get into a couple naming reactions now. So come over to the sideboard. And to start out with, I always like to review a couple reactions or concepts here. So let's see if you can come up with a name for this compound and that compound. And can you decide whether these are aromatic or not? Okay, so you can pause the video there. Okay, and then we're back. Let's see if we can get a name here. We need to number it in such a way we get the lowest possible numbering. And the thing here is there's no new parent here. The parent for this name is benzene. It doesn't have one of those functional groups that mixes. There's no aldehyde here. If there was an aldehyde there or somewhere, we'd call it benzaldehyde, right? If there was a methoxy group, we'd call it what? Anisole. If there's a carboxylic acid, we call it benzoic acid. But if there's none of those, if it's just alkyl, nitro, or halo, we just call it benzene. And then the lowest possible numbering, and then we alphabetize, right? So here we have nitro, fluoro, isopropyl. So which one would be first here? Right, fluoro, and it's at the 2 position. I won't draw it all out for you there. Let's see, isopropyl, do we alphabetize by the P or the I? Right, the I. You learned that before, right? So I comes next, I think, isopropyl, and it's at the 4 position, right? So you need that there. And then what, 1 nitro, benzene. So that would be the IUPAC name for that. How about this one? Do we have one of those special new parent substituents on the benzene? Yeah, we have the aldehyde. So this would be what, a benzaldehyde? Benzaldehyde. And on benzaldehyde, remember that always gets numero uno, okay? Whatever that parent name is, this means number 1 there. You don't have to put it there, it's redundant. If you do put it there, we won't take it off, whatever. But then relative to that, we have 3 and 4. Now we alphabetize, put them out here, what, 3 bromo, and then 4 nitro this time. Right. Did you get that? Okay, yeah, work a couple of those. Nomenclature's not a big deal for me. I like nomenclature though in that it helps you keep track of isomers, and that can be very important for reactivity and even mechanisms. So naming is important there, but don't knock yourself out over it. Just make sure you can keep track of the substituents and the isomers. Okay, the other key topic here, Chapter 17, of course, was aromaticity. We had the Hcl requirements there, and what were they? The 4n plus 2, right? Pi electrons, and those pi electrons have to be flat, continuous, and conjugated, right? So let's see if we can apply that here. Here we got furan. This oxygen has 2 lone pairs. Is that aromatic? Count up the electrons. 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons? Oh, is this aromatic or not? And turns out it is aromatic. If you look in the Pro-10 NMR, these are in the 7 range. So what's with these lone pairs? We must just count 1, right? And the other we don't count. Well, we can look at it sideways here, and there might be something on hybridization we need to worry about, right? So yeah, one of the lone pairs can be in a p orbital, p atomic orbital. So the oxygen's hybridized as what? right? sp2 hybridization. So one is perpendicular. That's like a lone pair on pyridine. Remember, we talked about that? And one is part of the aromatic hextet, but the other is perpendicular to it, and that renders this molecule, yes, aromatic. It's flat, continuous, and aromatic. What about this one here? We have an exo double bond here, double bond there and there, and what's here? A CH2. So is this a continuous cyclic array? No, not aromatic, okay? Criteria falls through there. What about this one? Here's an interesting one. 1, 2, 3, 4, 5, 6, 7, 8 carbons around the ring. We're drawing a donut here with an extra pair of electrons, and then it's 2 minus for the charge. You have to kind of draw this one out to see where the electrons are here. We'd have something that looks like this, maybe. It's cyclooctatetraene, which remember before we said was non-aromatic, right? But if we dump in 2 more electrons, and there are ways to do that, you just treat this with excess equivalents of sodium metal or lithium metal, and it'll actually dump in 2 extra electrons and make this structure, which is a dianion now. And it is flat. And if you take an NMR of this, guess what? These hydrogens on the side are where? Right around 7. So what is this? It's aromatic. How many electrons do we have in the ring? The 8 here plus 2 more means what? 10 electrons. So is it aromatic? Yes. We'll say exclamation point there. So that dianion can become aromatic. So you have to examine things and see. This is a tricky one. There are some problems at the end of chapter 17 that get into ions like that. All right, let's get into the main event, which is the electrophilic aromatic substitution. I'd like to do this using some examples right away of molecules that are made using electrophilic aromatic substitution. In fact, even in a complex setting here. If we could take aniline, there's aniline, and if we can sulfonate that, H2SO4, this turns out to be a bad reaction. I'll show you the alternative here. If we can form the sulfonic acid of that, of aniline, this is a sulfa drug. Okay, sulfonaniline it's called. It's a yellow material. It's an antibiotic material. In fact, it's one of the first popular antibiotics developed. In fact, it was used on the battlefields in World War I and II to prevent gangrene from setting in. When a medic would attend to a wounded soldier on the battlefield, often the first thing they'd rip open a little packet and this yellow powder would be spread over the wound. Maybe you've seen that in movies. Why'd they do that? Well, this is an antibiotic material. It actually mimics the effect of PABA in bacteria to make folate. So there's a specific mechanism of how it works. That was determined later on. This drug was developed over 100 years ago by Paul Ehrlich and others in Europe. And it came out of the dye industry where they were using these electrophilic aromatic substitution reactions. So this is a yellow compound. It does absorb in the visible range. This turns out to be a bad reaction. You can't do strong acid on aniline because you'll protonate it and form the anilonium cation. Then it actually becomes a meta-director, which is slow. So we'll say no here. Well, let me show you the alternative approach. You first form the amide of the aniline. And this is, an amide now instead of a free amine. This one now is a good ortho para-director. So we can sulfonate this easily. H2SO4. We can get the sulfonated form here. We need the sulfonated form on there, and it's not strong enough acid to take off the amide. The amide stays on there under these conditions. And then we treat with strong acid, and we can actually reverse off the sulfonate. Oh, sorry, we don't need that. We're not taking off the sulfonate group. What comes off first, if you have an amide versus a sulfonate and water, You can hydrolyze off that. Now that reaction is one that we'll cover later on. Okay, in fact, forming the amide. This is coming up in a later chapter when we get to carbonyl stuff. But this shows that this is a bad orthopara director. We can't do it directly. It takes 3 steps to make the sulfa drug. Okay, and what a wonder drug it is. It's saved millions of lives, actually, around the world. People often died from simple infections of the skin. And so this has been a real miracle drug, by the way. It was before penicillin and all the other more recent antibiotics that we enjoy, but this one is still approved by the FDA and still used for different indications. So you can see the aromatic electrophilic substitution right here to form that, and yeah, a couple more steps. Yeah, now how does this work? The sulfa drug is an antibiotic, and it inhibits the action or takes the place of PABA in the bacterium. And PABA is what? Maybe we've mentioned this guy before. PABA, there's a mouthful for you. What does it stand for? Para-aminobenzoic acid. And this goes into folate. Okay, this is a substrate for folate in the biosynthesis. Don't have time to go through all that, but the sulfa drug mimics this and actually binds to the folate synthase more tightly than the endogenous substrate here. So this inhibits the production of folate. And if folate's not produced in the bacterium, it dies. So this is a mechanism that's selective for that. We don't have a folate synthesis pathway in higher animals, so this is not toxic to us. And that's the basis of how drugs work, right? You want it to be toxic to the pathogen, but non-toxic to the person. Okay, maybe that seems obvious, but you see how the drugs kind of relate to that now. So there's an important one that we can see. We'll go through later on the synthesis of PABA because we've got to put on a benzoic acid on benzene, and then we've got to get a nitrogen on there. We're going to do it indirectly, though. First, we're going to make toluene. We're going to use that chromium acid oxidation. Later, we're going to nitrate and then reduce the nitro to the aniline. So these steps are useful and productive. Both PABA and sulfur drugs are made on ton scale around the world. So you can see how these are important. All right, let's get to the main event. Electrophilic aromatic substitution, what do we need to know there? Well, the basic mechanism, if you can keep the mechanism straight, you're going to win 90% of the battle, okay? So let's keep this straight. But first, let's look at this, right? What we've done before, an electrophile adding to an alkene to form a carbocation. And then we've had some sort of a nucleophile add here to give what? The substituted product, right? So there's an electrophile adding first, give a cation, and then nucleophile tag. That's 351 chemistry, right? Now we've got this. And this is the difference, right? We got the same electrophile coming on, and this step's completely analogous, right? So what do we get to? Well, we get to a cation. Cation's a little bit different, right? It's allylic. In fact, it's conjugated to 2 pi bonds. So that's going to let that go, okay? But notice it's not aromatic anymore. This was aromatic to begin with. This is not aromatic now, okay? So this is why we went over the aromaticity. So if this was analogous to 351, we just have the nucleophile attack here, right? But we're not going to do that. What are we going to do? Here's the departure, right? We're going to have something that's basic enough, and it doesn't have to be a very strong base. This is actually very acidic now. Why? Because if we can pull that proton and release those electrons back, what do we get? We get the substitution product, and the hydrogen comes off, and the electrophile takes its place, okay? And we re-aromatize the product. So all these electrophilic aromatic substitution reactions are going to follow this pathway, which is analogous to what you've learned before up to this point. But then we got to add in this aromatic effect, okay? So what is the electrophile? That's the question we need to answer for these 5 reactions, right? Let's see. Let's do nitration first. And then we'll do sulfonation, halogenation, and then the Friedel-Crafts. So we've got the 5, and we're going to go through each one separately, right? So here's the key reaction. Benzene, nitric acid, sulfuric acid. Yeah, it's a combination of those two. Very corrosive, very reactive. Get any of that on your skin and you're in trouble. Okay, these have to be contained very carefully here. If you do it carefully though, you get a very high yield. Things can vary depending on the scale, whatever, but the nitrobenzene product is over 90% in most cases. And it can be easily distilled or separated out from maybe some unreacted benzene. But remember, benzene comes from coal tar. It's very cheap, easy to get a hold of. And the nitro product is very useful. We have a carbon-nitrogen bond. We can reduce that to the aniline that we'll see later on, either with hydrogen and palladium or tin and HCl. There's a couple ways to reduce the nitro, but we're just doing that part now. What's the true electrophile? We look at that and we really can't tell. Let's draw out the structure of nitric acid. There it is. If you remember your Lewis dot and your formal charges, make sure you can do all that. Why is this nitrogen plus charge there in the middle? Nitrogen has 5 valence electrons minus how many bonds? 3, 4. And there's no lone pairs on there, right? So what's the charge? Yeah, +1. What about this oxygen here? It's got 3 lone pairs. Why is it negatively charged? Well, oxygen has 6 valence electrons. How many bonds are shown here? 1. How many lone pair electrons? 6. So what is it? It's -1. Make sure you remember how to do that. And if you're uncomfortable with some of these steps, make sure you draw out the full Lewis dot structures that way. So what does sulfuric acid do? Well, H2SO4 is a stronger acid than nitric acid. Nitric acid has a pK of about -2 in the very strong range, right? Sulfuric acid is even stronger, -5, super strong acid. So believe it or not, nitric acid can get protonated by sulfuric acid. Now that might look kind of weird, but this is a stronger acid, so this is the better proton donor. And we can protonate nitric acid. I know that looks kind of funny, but believe me, it works. So we get 2 oxygens on there. And we still have the negative charge, plus charge there. And what do we have here? Oh, we have a plus charge. Now that should bother you. This is a high energy intermediate. Why? 2 plus charges next to each other? That's not good. But we're one step away from losing what? Water. So let's go ahead and do that. What do we get? We get this species. And what just came off? Oh, H2O. There you go. So we get these 2 things, water and this guy. What do we call this? This is nitronium cation. Nitronium meaning something that's charged, and the O means it's the higher oxidation state cation. We'll see nitrinium or nitrosyl cation later in the course, but this is nitronium cation that arises from protonation of nitric acid and loss of water. This is the true electrophile. Okay. Let's see. So can you follow that okay? This is all kind of inorganic nonsense, right? We're not involving carbon. I've never put this mechanism on a quiz or a test, but I like to show you the inorganic chemistry behind it. Now, let's get to the organic chemistry, right? So let's take benzene. And benzene is going to do what? It's going to attack and push the electrons over there and form our nitration product. Okay, so that's our true electrophile. That gets attacked. The benzene is indeed a neutral nucleophile. And this is a very powerful, strong cationic species, the electrophile. It's electron poor. Why? Because we can push the electrons in there. It's bearing a plus charge on the nitrogen, and we can push the electrons out toward the more electronegative atom, oxygen. Okay, so there's a couple things to look at there. So if you want to look at the model, I've got it right here. Here we've got benzene. And here's, pick any pi electrons, they're all the same, right? So here's our electrophile, and the electrons come out and attach onto the electrophile. This rehybridizes, we'll get to that in a second, and then we have a cation here that's stabilized by the rest of the 2 pi bonds here, okay? So we've put on the electrophile, and now we've got to examine this intermediate, okay? So what do we get? We get our electrophile on there, our nitro group. And, don't forget what a nitro group looks like. There it is, nitro. And I'm drawing the whole thing out with the opposite charges. That nitrogen is still plus charge. Why? Because we put electrons in and we pull the electrons out. So it's still 4 bonds to nitrogen. It's still plus charge nitrogen. And O minus now because we push those electrons out onto it. So this part of the mechanism you need to know, okay? You need to know for nitration, it's nitronium cation and the flow of electrons here. Okay, so what we could do here, we've got water, we've got nitrate, we've got sulfate. We could have those nucleophiles attack here, right? Analogous to 351. Well, what are we going to do different now? We're going to take this proton off. What base are we going to use to take that proton off? Well, there's a couple. I just mentioned them, right? Nitrate, sulfate, or water. Which one do you think is better? Actually, water is better. Because water, once it's protonated, forms hydronium ion. That pKa is about 2, right? It's about the same there. So let's go ahead and grab the proton there, free up the electrons, and see what we get. Oh, we get the product. Yay. We got the nitro group, and I'm just abbreviating it now. We get back the pi bond here, and what's our byproduct from this? Yeah, H3O plus. That's hydronium cation, and that's okay, even though that's also a strong acid. We're in the presence of super strong acids, okay? So you could use nitrate or sulfate here, but you'd be going to a stronger acid. I prefer to use the stronger base, which gives a weaker protic acid in this case, the nitro group there. Questions on that? Does that look okay so far? There is a form of nitronium cation that is not acidic, that can be used under non-acidic conditions. And it's this right here. It's nitronium tetrafluoroborate, it's called. This is a salt material. It's a nice, well-behaved material. It's kind of expensive here. But if you want to do a nitration under non-acidic conditions, you can actually use nitronium tetrafluoroborate to do nitration. And you see it's part of the salt. There's the true electrophile. And here's a non-nucleophilic salt, a counter anion that can be used to do a similar type of reaction. A lot more expensive than nitric acid, sulfuric acid, but maybe we'll see that later. I don't know. We've got some alternatives. When we do dye substitution, there might be a way we'd use that. All right, we okay with that one? We've got nitration. Now let's do sulfonation. And stay on the same board there. Sulfonation. We're going to take benzene again. Different reagent now. It's just sulfuric acid or sulfur trioxide and acid. And the acid can be more sulfuric acid or it can be HCl. Sulfur trioxide is a neutral material, okay? And instead of the strong acid here, you can add in some acid to activate the sulfur trioxide. We need to see what the true electrophile is. Or you just use sulfuric acid itself and you get the sulfonated product. And let me draw out the whole thing so you see it. So that we call benzene sulfonic acid, and it has the sulfur carbon bond right here. This is one of the unique reactions in that it's reversible. If we heat this up with HCl and water, or heat it up with sulfuric acid and water, you can actually go back to benzene and the sulfur trioxide. It is reversible, okay? And sometimes we want to put on a sulfate group to activate maybe the meta position or to block an ortho or para position. We'll see dye substitution why sulfonation can be important. But there's a lot of applications of aromatic sulfonic acid. So how are we going to do this? Let's see. We're going to protonate sulfuric acid. And again, this looks kind of funny. And we're going to use sulfuric acid to protonate itself. So this is a auto-protonation effect. Let's see, here we've got H2SO4. I'm not going to draw out the other one, but this is the acid we're going to use here. Here's our base. Let's go ahead and protonate that. Okay. And what do we get? Protonated form should look like this. Okay. We've got an extra proton on there. And what? This is one step away from making, yeah, water. And what do we get? Sulfur cation and water. Okay. Now, there's another way we can make this. We can take sulfur trioxide and we can put a proton on there. Okay. So that's the alternative conditions here. Sulfur trioxide looks like that. It's neutral. Sulfur can expand its valence shell, right? It's a third row element. And so, yeah, you can go over to that. You can move the camera over here if you'd like. Get away from the, the sink there. But yeah, so you can, see the loss of water right there to form the sulfur cation, sulfonium cation. Or you can take sulfur trioxide and just protonate here. And pulling the electrons out gives the same thing, okay? So what do we do here now? Well, we just do the same thing. Let's use a pair of electrons here in benzene, attack the sulfonium group, and we get the same thing there. We get this. And we've got that hydrogen still on there, okay? The hydrogen is still on there where we attack the electrophile. And what's right here? We pull those electrons out to grab the sulfur cation. Yeah, right there is our cation, right? Okay. So that's important to look at. And then how do we get there? Well, we can use water to take off the hydrogen, the proton on the side there. Push the electrons back down and we get to our product. Okay, so these steps you need to make sure you know and know what the true electrophile is. It's the sulfonium cation right there. Okay on that one? I think we're all right. The reverse I won't show you now. The reverse here, you just put a proton back on there and then lose sulfur trioxide. I'll show you how to do that later. But it's because the sulfur carbon bond is actually quite weak, and so it can be reversed. And sulfur trioxide is actually quite stable, so that can be reversible. That's one of the unique ones. All right, let's do the other couple reactions. We've got halogenation, and we got to get to Friedel-Crafts. So halogenation is bromine, chlorine. Here, I'll just show it for bromine, Br2, and then ferric bromide. Need to have the ferric bromide. If you leave that out, no reaction. So you've got to have the catalyst in there, and then you get the monohalogen product. Okay. Now you can also use chlorine, okay, Cl2, but then you use ferric chloride. What about fluorine or iodine? Fluorine is actually too reactive. F2 is an extremely reactive, powerful oxidant that actually leads to explosions if it's exposed to organic compound. So we don't form aromatic fluorides that way. I'll show you another way to do it. Iodine in some cases will work, but it's often reversible in that the carbon iodide bond is relatively weak. We'll see another way to make that via diazonium ions later on. Okay. So what's up with this reaction? Let's look at the reagent. What's the true electrophile? We can't really tell, right? It's not going to be direct attack onto the bromine here, okay? We've got this aromatic grouping of pi electrons. This is not as good a nucleophile as a simple alkene. We've got to activate this. So let's put the lone pair on the Lewis acid. And this is called a Lewis acid Y because it does have extra empty d orbitals here on the transition metal. So this is an empty orbital. Lewis acid definition is what? Something that can accept a pair of electrons, okay? Let's go ahead and form that and see what that looks like. It would have bromine with 2 bonds to it now and FeBr3, okay? We just made that bond. Do we need to worry about something else on this structure though? Yes, formal charges. So if we have a bond here to bromine and then count it up, we still have this lone pair here. What's the charge on that bromine? Yeah, it's +1. Ah, there's another charge here too. If we put some extra electron density on this neutral iron chloride, what's the charge on this iron, right? It's -1, okay? So we have that bromonium ferrate, it's called. Now, where's our true electrophile? Well, you might be tempted to say it's right here. That's the positive thing. Let's just attack that. You can't do that. This bond is relatively weak. It's pulling these electrons here. So what does that mean? The true electrophile is this bromide on the end. And let's go ahead and flow the electrons here and see where they end up. You see, by making a bromonium ion cation here, it's weakening this bond even more. It's already a pretty weak bond. But when we attack here, then we can push those electrons over. You can actually use an MO, a molecular orbital designation here. This sigma bond becomes even weaker if this is positively charged, and the sigma star actually lowers in energy and becomes almost the same energy level as the filled orbital in benzene, the HOMO. And that's what's acting, the HOMO with the LUMO here. Sigma star is what's in the tank. But don't worry about that. Let's just see the result here, the flow of electrons. What do we get? Bromine's on there now. We still have that hydrogen there, and we have the cation there, okay? And what do we have here? We have bromine onto the iron. There's 3 there, and it's still negatively charged. So overall, see, we're still neutral for the system, right? We have the cation here and the tetrabromoferrate right there. So what are we going to use to take off this hydrogen? Do we have water in here? What's going to be our base this time? A little bit different, right? Yes. What if we take out the bromide off here? Yeah, that would be the negatively charged bromide. And is that a strong enough base to take off this hydrogen? Yes, it turns out it is. This is an extremely acidic hydrogen. They've estimated the pKa's of these. Once you put an electrophile on here and you have the cyclodienyl cation, this is in the negative range. So you can easily use a weak base to take off that proton. So let's just do that. Let's take that off, dump the electrons back down, and what do we get? Oh, we get our product, bromo or chloro, benzene, and then let's see what the result is. Oh, HBr. And yes, these reactions do get acidic. The pH goes down in these solutions. You can add an extra non-nucleophilic base to neutralize that, but we're not going to worry about that. And then what? You get back the ferric bromide. Okay, so there we get our product. You could go through the same thing with chlorine and get the same product there. So hopefully that looks okay there. Yeah, all right, let's get into Friedel-Crafts. This is, some people have argued this is one of the most important industrial reactions ever developed because of the variety of products making carbon-carbon bonds with Friedel-Crafts reaction now, like I mentioned. And the versatility of all the products that come out of this, not just drugs and dyes and high performance materials, also fuel materials, high octane aviation fuels. In fact, some people argue that some of these aviation fuels that the Americans and the British had via the Friedel-Crafts reaction actually won World War II. Any history buffs out there might remember the Battle of Britain. The RAF, the Royal Air Force, was fighting off the Luftwaffe Air Force. And the Spitfire planes could actually rev their engines faster. They could climb faster and outmaneuver the Messerschmitt 109 fighter planes of the Germans. So Churchill famously, at the end of World War II, uttered that famous phrase, "Never before in the course of human history was so much owed by so many to so few." And that's kind of a tortured way of saying that, you know, those poor pilots and the people who developed the fuels and the radar systems fought off the Nazi invasion of Britain. And if Britain would have fallen, the world would have been very different today, right? So I'll point out a couple of these fuels that are available from the Friedel-Crafts reaction. But Friedel was a professor at the Sorbonne in Paris in the late 1800s, and James Crafts was an American postdoc. He came back to America and founded the research efforts at MIT. So he became the president of MIT, actually, James Crafts, the American. So this chemistry is kind of neat historically and versatility-wise, whatever. But let's look at the main event. Enough of me talking. Let's look at tert-butyl chloride and aluminum chloride. Now you have to have the Lewis acid, and it's aluminum Lewis acids now. And alkyls work here, all sorts of alkyls, as long as they're sp3. Primary, secondary, tertiary work. The mechanisms are a little bit different. You cannot have sp2, okay? You can have bromide or even iodide here. You can't have fluoride. Fluorides, those are too strong bonds. So, and you can have other ways of activating and seeing the true electrophile. In fact, you can already kind of tell what's going to be the true electrophile here because the product is tert-butyl benzene, okay? So, you know, how did we get there? Well, we're going to form a tertiary cation, okay? You could already kind of see that, right? If it's a primary pathway, we're not going to go through a primary cation. We'll have to modify the mechanism a little bit. But there are other ways to make cations, right? So I'll show you a couple alternatives here to Friedel-Crafts. But here's the basic thing. So let's see, it is a Lewis acid. So let's go ahead and coordinate the lone pair there. And what does that look like now? Right, it's the illuminate. We're going to illuminate the illuminate. Okay. And what do we see there? We see the cationic form there. And we can break this bond. That bond becomes even weaker here. And what do we get? We get the tert-butyl carbocation, which is tertiary. And we get aluminum chloride. And I'm going to keep that one aluminum out there. And we've got the illuminate salt because we're going to use that chloride here in a second, just like we did for halogenation. But what do we do now? We react with the benzene. So there's our electrophile. Same thing here. We're going to get the carbon-carbon bond on there. Oops, don't want to do that yet. Hydrogen, tert-butyl group, and cation. Okay. Now, how do we get to the product? Right, we need to use chloride here. And I'll just draw it up here. Chloride right there to go to the product, okay? HCl, yeah, is a byproduct. These things do get acidic, but we form the alkylated product here, okay? So that's with the tert-butyl. Primary, secondary are okay, but let's look at one that's not okay right away. So that one is fine, but here's one where we're going to have a problem, or at least something's going to be different. Let's look at this one where we have a, what? An isobutyl thing. Same thing, aluminum chloride here. And you might think, well, okay, you know, he said primary is fine. We're going to get that. I'll put a question mark there. It turns out that's not the product. If you use this isobutyl now, that has branching, oh, there's a hint for you. We don't get the isobutyl product. We get what? We get out tert-butyl again. Oh, what happened? Oh, a rearrangement. Okay, those of you who read ahead. And maybe you remember rearrangements from 351. We saw that a lot of times with carbocations next door to what? Branched positions. And my corollary there is if it can rearrange, it will. And the major product will always be the rearrange thing. If you can go from a potential what? Primary cation position, have a migration here and give another product. So let's look at the mechanism here of this rearrangement. And it starts here from the illuminate. So if we've got this, you might think, well, we can just pull that off, but that would be what? A primary carbocation. Instead of staying there, when this comes off, what happens? This migrates over. We have a 1-2 shift, we say. And what type of shift is it? It's a hydride shift. Now, you don't see H minus with 2 electrons on it there, but you have this, what? Sigma bond right here. And because it's branched right here, and because the result of that migration leads to what? Leads to the tertiary carbocation directly from that 1-2 shift. And here's our migrated hydrogen, right? There it is right there. That one can migrate over to the tertiary carbocation and give us, again, the branch product. So If we have these primary type groups, we often get this migration effect. We can't get these type of primary aromatic compounds directly. And that's very similar to what we've seen before with other carbocation intermediates. How about this one? Here's another one to keep in mind. How about just the primary straight chain one? Okay. And you might think, well, okay, this is primary. Yeah, but there's no branching here. What's going to go on with this one? Well, we can still have that same adduct there. I'm not going to draw it out, but you've got hydrogens here that can migrate over. Guess what the product is here? Again, like this one migrated to give the terp-butyl. This one will migrate over, and you'll get the sec-butyl. Okay, so here's the primary butyl, right, or the N-butyl one. This gets a sec-butyl. So how are we ever going to get this? Well, we'll see coming up. We're going to have to do Friedel-Crafts acylation first, and then reduce the aromatic ketone there. Okay, so right now, all we know is how to make these branched ones from either the straight one or that, or directly from the terp-butyl chloride. So we've got some limitations already showing up here. Well, do primary work at all? So let's see here. We're going to have to back up a little bit and look at the reaction. And yes, primary can work. If we have benzene with iodomethane, this is a good one. And you can use the same aluminum chloride here. It's okay to mix up the halides. And this one will give a good yield of toluene. Okay. You can also take the ethyl one, aluminum chloride, and create the ethyl benzene. Okay. Now, propyl is a little bit different. If you try to do propyl here, guess what the propyl will do? Now that's N-propyl. Okay. So if you have this coordinated, what can shift over here and make a more stable carbocation? This one, if the hydride shifts over, that's still primary. In fact, these will go with different mechanisms. We'll see that in a second. But if you have the N-propyl, what do you get here? Not the N-propyl benzene, not the straight chain. You get, right, the isopropyl again. So Friedel-Crafts, sorry, it's a little more complicated than the first couple of reactions. This one gives us some extra stuff. Let's look at these two here. Let's take the lone pair here, coordinate with the Lewis acid. What do we get? The iodide, the aluminum, and what's our charge there? And our charge is on iodide. So there's our intermediate. There's our true electrophile for the primary ones. These don't form the carbocation right away, and they can't rearrange to a more stable carbocation, methyl and ethyl. They'll just stay there. You can't rearrange ethyl. There's no isol ethyl right? On either end. It's just ethyl. Same thing with methyl, but N-propyl is different, right? You can have the migration, and then it's at the middle position becomes more stable carbocation. So that one does rearrange. These here go through these complexes here, and the complex is actually what is the electrophile. So it's more of a direct attack. It's more SN2-like, let's say. Where the other ones that are more stable carbocations, secondary, tertiary, are what? More SN1-like, okay? They form the stable carbocation. This one is direct attack onto the primary position, which is best for what? SN2, right? The strong nucleophile. This isn't a very strong nucleophile now, but the direct attack there goes to what? You get the methyl on there, the hydrogen, the cation, and yeah. And then you got the rest of the thing here, right? Chloride can take off the proton and give you the product, toluene in this case, okay? And ethyl works the same way. You can do ethyl here, then you've got an extra methyl there. It's okay. You can't rearrange it to a more stable cation, but this one you can. So you can do the mechanisms of those, I think, on your own and come up with the right thing. Now, one other thing I should mention, especially with methylation, guess what? This is often a minor product. When we methylate here, and this is kind of telling you that Dye substitution not only can occur, it often occurs. When we put an alkyl group on benzene, that's electron releasing. That makes the benzene more electron rich. And if you have any excess here of either of these reagents, you can get dimethyl, both the ortho and the para, and you can get trimethyl, which looks like this. You can even get tetramethyl products. You can get pentamethylated benzene, and you can even get, yes, hexamethyl benzene. Ouch, why is that? Because progressively, as you add more alkyl groups, the benzene's getting more electron rich. And the electrophilic aromatic methylation from the more substituted one actually becomes faster. And normally, if you want to do that, you add the amount, excess, whatever, control the time and the temperature to get that. Yeah, you can get a decent yield of just monomethylated, the toluene product, but it's sometimes tricky to do. We actually get toluene from pine oil, tall oil it's called, from pine trees. It's distilled out of there. So there's actually another source for that. But this does work, okay, the primary methylation. Okay, let's see. Let's do a couple alternatives to the alkylation approach, and then we'll probably do acylation here in part 2. Okay, the Friedel-Crafts acylation. Time-wise, I think that'll work out okay. Let's do some alternatives to the halide. There are other ways to form carbocations, so let's see how we can do this. You can take benzene, and you can react it with cyclohexene and acid, sulfuric acid, and guess what? You can get out cyclohexyl benzene. Okay, this isn't Friedel-Crafts from the halide, although we could do the halide. We could have chloro or bromocyclohexane, but here we just have simple cyclohexene. How does this work? Well, yeah, we know how to protonate alkenes, and so this kind of combines 351 here with the new topic of Friedel-Crafts. Then once we have the carbocation, we get that from the chloride or the bromide, right? Now we can attack, and there's an extra step of losing the proton there, right? So we get the cyclohexyl on there, the proton, the cation, and then what? We can use sulfate or water. Got any water in there to take that off, give the product. Okay, so alkenes often work for Friedel-Crafts alkylation also. Let me show you the main fuel material in World War II. Like I said, the Allies, the Americans, and the British had this procedure at refineries in New Jersey. They made all sorts of this material, shipped it over to England, and they made cumene. Cumene is isopropyl benzene. And cumene has an octane rating of 118. So if you blend it in with lower octane fuels, you can create a higher, more efficient burning gasoline material. And this is one of those compounds that they say won World War II. And it's using HF, which is a relatively weaker protic acid, and what? Propene. So you need to protonate this, form the secondary carbocation, and then that attacks. So the mechanism I'm not showing here. But this was scaled up to make many tons, and then it's still used in aviation fuel today to boost octane, whatever. But that's cumene. Cumene is also used to be oxidized to phenol, and the byproduct is acetone. In fact, most phenol and acetone are made from the oxidation of cumene, which is kind of a neat process. Makes two different things there. Let's see, one other way to make our alkylation products is to use an alcohol. So here is 1 butanol, and we're going to use a strong Lewis acid, boron trifluoride, and you could use other Lewis acids here. This will coordinate the alcohol. I'll show you a little bit about the mechanism, and it puts the butyl group on there. But this is a straight chain butyl, and guess what? It does rearrange. You form the secondary butyl product, okay, from this. And so what does that look like? Let's see the intermediate here. Well, the intermediate looks like this, the coordinated alcohol on the Lewis acid. So our BF3, the boron, would be a borate, and what? This would be positively charged, right? Okay. Well, we can then ionize this off and shift over the hydride, and what? We get the secondary cation, right? And there's our true electrophile that again leads to the shifted over alkyl. Okay, I think that's I could show you the styrene synthesis. Oh, and I need to do that. Okay, one more topic on this one. I think we're okay time-wise. A little bit more time. Okay, a little bit more here, and we'll get the second hour later. Don't worry. Let's look at this. So you can do the ethylene with HCl and aluminum. Actually, the two are needed together here. I'm showing you the industrial process for making styrene, which is made on very large scale. John Huntsman, the famous Mormon industrialist, made billions of dollars off this. In fact, he cornered the world market on styrene production. The first intermediate, though, is just ethyl benzene, okay? And that's just with ethylene, benzene, and a mixture of HCl and aluminum chloride to make ethyl benzene. I think that's okay. To get to styrene, though, and styrene, remember, has the alkene there, right? Styrene, making polystyrene and all sorts of other materials from styrene. We need a double bond on there, right? So what do we need to get rid of from ethyl benzene to get to styrene? Yeah, we've got to take off hydrogen, okay, the two hydrogens. How do we do that? Well, I'm not going to show you the mechanism of this, but it's zinc oxide and 600 degrees. It's an industrial process, and you have to be very careful to keep oxygen away because those things are, what, highly flammable. So don't worry about the mechanism there. But it's a dehydrogenation reaction, similar to hydrogenation with palladium. In fact, other catalysts will do this. But yeah, don't worry about that. But it shows you that. But this points out, how come we can't go directly from benzene to styrene? What would we need? We'd need this, right? We'd need a vinyl chloride and aluminum chloride. Why can't we just do that? I said it was limited to sp3, right? Alkyl halides. Why not this? Let's see, I can draw this. And if I can draw the mechanism, it must work, right? So what's the problem here? Aluminum chloride, this will be the aluminate. This will be plus charged. How come the benzene can't just now attack here? What's the problem? There's a couple things, right? Did we say when we covered in 351 SN2 reactions, did we say that vinyl or alkynyl leaving groups were okay? No, we said those gave no reaction. Why? This is sp2 now, right? This is a stronger halide bond. These are held closer to the carbon nucleus, right? There's 33% S character here. So these are stronger bonds compared to sp3. What's the other thing here? Well, the approach, right? You could say, well, let's ionize this and make vinyl cation. Again, that's bad compared to alkyl in its primary. So there's a couple bad things there. It's not going to ionize first. Well, what about just direct attack on the back here? Well, that's coming in coplanar with these hydrogens that are blocking the approach to that sigma star. So sterically, these are slowed down. Electronically, they're slowed down due to the relative stability of that. And they can't ionize to primary. So there's 2 or 3 things you can point to, which means no reaction here for this, okay? Vinyl halides will not work. So styrene can't be made directly. You've got to put on the ethyl and then dehydrogenate. Or we'll see another way. We can halogenate and then eliminate. That's 2 steps, actually. So that'd be 3 overall. Industrial, this is how it's done because this is a good process. Plus, you can use the hydrogen gas, the byproduct, for other things. So a couple things there, but stay tuned for that. And stay tuned here. Our next session, part 2 coming up. Second hour today will be Friedel-Crafts acylation and dye substitution reactions coming up. So very good. Let's take a break right here. Thank you.